All right, calculus folks, here we go. You've got this warm up in front of you. Hopefully you've tried it. I'm going to try and take it up real quick. This is the idea of absolute maximums and local maximums. And I'll let you have a look at my answers here in a second. A reminder of the difference. An absolute maximum is like the overall highest that it goes. So in this case, it's this point right there. That point right there is as high as the function goes. So it's an absolute maximum. The absolute maximum is the output value when x is the input value. So we call that the maximum value, but we also say where it occurs. And notice that there's also local ones. So locally, close to the values around x equals 4, that's the maximum locally. Like close to the values near x equals 4, it is a maximum. And so one way we could think of finding the absolute maximum is get all the local maximums together, get them all together somehow, and then just pick the highest one. And we can do the same thing for absolute minimums as well. And we'll see. Sometimes, you know, we've been practicing finding those points, right? Because that's when the derivative is equal to 0, the maximums and minimums. But sometimes the absolute maximums happen at the endpoints. And I wanted to point that out. This one, the absolute maximum happens at the endpoint when x is minus 4. But sometimes it doesn't. Like over here, the absolute maximum happened when in the interval where the derivative was 0. And we can keep going. Here's some more. This is just more practice. I'm going to pause if I'm going too fast. And check my work. I might have made a couple of errors in here. I've been known to make the odd error. For this one's interesting. So the absolute maximum, the highest the function goes, is right there at x equals 2, because that's just the highest output value. Local maximum, well, certainly compared to the values that are near x equals 2, that's the highest, right? There's our absolute one. But there are also two other local maximums, one at a spot where we have a horizontal tangent, and one at an endpoint over here. So there are 3 local maximums in this one. I wanted to point out that the absolute minimum, which is right there, that's the absolute minimum, that's actually the only minimum. You say, well, there's got to be a local minimum over here. Well, the discontinuity means I can get as close to minus 1 as possible, but I can't say the local minimum there is minus 1 because the function at x equals 4 has this output. Because it's discontinuous there, I can't say that this point is a local minimum. I wanted to point out, we talked about this one in functions as well. No minimums or maximums on this, right? It keeps going up forever. There is no maximum. And similarly, there is no minimum. If I am asked to consider the absolute minimums or maximums only on an interval, then I'm going to slice off this function that's given and pick out the minimums and maximums just on the piece that I've got. So the absolute maximum was right there, and that happened to occur at a horizontal tangent when the derivative is 0. But the local maxima is this one. Local maximum 1 at minus 2. 1 at minus 2. Oh, that's not it. That should have been down here, right? 1 at minus 2. See, I did catch my mistake. The odd times I do. The only maximum here, the only local maximum is at that one that we identified there. But the absolute minimum happens at an endpoint. There are no spots in that interval where the derivative is equal to 0 that would give a minimum. Notice that if I expanded my interval, yeah, okay, there's a local minimum, and there's actually the absolute minimum for this function, or at least appears to be, but it's outside of my range. And so the idea is, if I wanted to find the minimums and maximums for a function, given the graph, yeah, it's easy. I can just point to the spots where it's minimums and maximum. But of course, we're not going to be given the graphs all the time. We have to figure out how to do this. And it's actually a pretty simple procedure. And here, maxima and minima, that's the plural of maximum and the plural of minimum. Okay, maxima and minima. And this sounds important, and it is. This is big chunk of the remainder of this chapter already is optimization problems. But it'll be a day or two before we get to the problems. Here, we're just looking for algorithm for finding maximums and minimums when we're not given the graph. So it says, this leads to an algorithm for finding maximum and minimum values of a function on an interval a, b. So we know maximums and minimums happen when the derivative is equal to 0, right? And we discard x values not in the interval. So the idea is I'm going to take the derivative, set it equal to 0, solve that equation, and any of those values that fall outside, so here's where the derivative would be equal to 0, but it's not in the interval, so I discard that value. Okay, so nice. Then I got to check the endpoints, because we also saw that minimums and maximums can happen on at the endpoints. That is, we calculate the output value at A and the output value at B, and then compare the values you found. That's the idea of we've collected between these two, we collect up all the locals and then pick our min and max. Easy peasy. And it says be mindful of discontinuities. So we have to be careful in case something like this happens or something like this happens, even though it's not common. Here we go. Find the extreme values on each function. So in this case, let's do the first thing, which is take the derivative, negative 3x squared plus 12x, there, 0, and then set this equal to 0. Because minimums and maximums happen where the derivative is equal to 0. Solve this. Let's see. Pull out an x. I was trying to pull out a 3, but 3 doesn't very often go into 16. So let's pull out an x. And I get 3x plus 16 equals 0. I get x equals 0, and x equals negative 16 over negative 3, or 16/3. Okay, so that's kind of like step 1 in our algorithm. Right? Are these values in this range? This one is, and this one is not. This one is not. This is 5 1/3, so I can discard that one. I don't have to include that one. Good. Less work, right? I goofed. Did you see that? Were you screaming at me? Yeah, you were screaming at me. Okay. This should be, because when the 2 comes down, that's 12. Thanks for correcting me. Thanks for that. I was 2 minutes later. That's 12. And of course, what's going to happen now? Yeah, it's going to be in our range. Darn it. Darn it. All right. So that's going to be negative 12 over 3, which is positive 12 over 3, which is 4, which is indeed in our range. So we have to include that one. So, and then it says check the n values. Well, okay. I also need to put, so these are kind of like my table of possible candidates for absolute maximum and minimum. So I have 0 and 4, and I want to calculate those values. So I put in 0 in here, and I get 5 out. I put 4 in here, and I get 37. And then I also have to check the endpoints, which is x equals minus 3 and x equals 5. X equals minus 3 and x equals 5. And so I put those into the calculator, and I get that one's 86. And I get that this one's 30. So what do I have? Well, it looks like that's a minimum. Right? That's the lowest value. It's the minimum. This one's the maximum. So what happens with these other ones? Well, this is a local max, right? Because it was 5, and that went up to 37, right? And then it goes down to 5. By the time it gets to 5, it's down to 30. This is a local maximum. And this one would be a local minimum, right? Because it was at 37, and by 5 it went down to 30. We chopped off the function there. And if we wanted to The a minimum of 5 occurs when x equals 0, and a max of 86 occurs when x equals -3. Okay, we didn't use a sketch, but let's do a quick one. Why not? What does this function look like? It goes through 5. 0, 5 was one of our spots. That was actually our minimum, which makes sense because if I just forgot about the 5 and graph this other function, which is easy to graph, then it has zeros at 6 and at 0. So it would here, I'm going to do this in a different color. Actually, I'll do it in red, and I'll move this one up. So this function, and it starts high, ends low. This is g, bounces and goes through. And then this other function is just this one moved up 5, right? And so if I had my cutoff, this was at 6, right? But my cutoff was at 5. It didn't get back down as low as 5, obviously. And then at 4, it had the maximum value of 37, right there. So the minimum happened at the beginning. The maximum was in between the interval. And there we go. It matches the graph. Isn't that dandy? Looks like my happy face has got a nose this time. All right, another one. Well, same thing. Let's take the derivative. The derivative happens to be, it looks like this is a quotient rule, doesn't it? You know, I suppose I could try and divide that in or do something goofy like that, but I want to find the maximum interval on this one. I'm going to take the derivative. Derivative of the top, right down the bottom. Right down the top, derivative of the bottom. All over the bottom squared. All right, and so tidy this up. Is there any factors? Can I factor the top? No, I think I have to expand. I'm going to expand everything on the top. That's 2t squared plus 2 plus 4 plus 6t. Tidy, 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 tidy. This 1 is okay. There, tidy this up. Multiply through by the -1 all over this squared. And so there's the derivative. Almost. Let's collect like terms. Plus 4t minus 12 all over t plus 2 squared. Okay, just going to check my notes, make sure I didn't goof anything up. T squared plus 4t minus 12. Yeah, okay. And I see there's a discontinuity, right? If I get that as one of my maximum or minimum values, and look, it's not even in our discontinuity isn't even in our interval, so we're okay with that. And so then, what do? There's my derivative. I have to set this equal to 0, right? And how do I solve that? Well, it's been since functions I did that. As long as this isn't true, I can multiply through by t plus 2 squared, and then I've got a little quadratic equation to solve, and I bet you it factors. Restall's ones are always factorable, aren't they? Well, not always. Sometimes you got to use the quad formula, but 6 and minus 2, so I get t equals -6 and t equals 2. Notice this one, the -6 is out of our range, right? So I don't have to worry about that one. So this is not an interval. And so from my derivative, I just have the one value that I can add. These are like the candidates. These are the possible candidates for minimum and maximum value. So t equals 2. And notice this is a common calculus student mistake, is the minimum or maximum is of the original function. So I got to put this back in the original function back up here. And that's always a little bit of work, but you jam that into the original function, and I think you get, looks like 6. And just use your calculator to do that. And so that's the first thing. The second thing is check the endpoints. Check endpoints, which are when x equals, not x, t, I suppose. T equals, I can't remember the interval, 0. Oh, 0 is a fun one to check, isn't it? It's easy. So that's when t is 0. We got 16 over 2, which is 8. And then the other endpoint is 14, which you can do that calculation. A little more involved, bigger numbers, but you should get 15. I tried that. And so what do I got? Well, there's the minimum, right? So it happened that the derivative was equal to 0, and that actually ended up to be the absolute minimum. It's the smallest of all these, and there's the maximum. So a maximum of 15 occurs when t equals 14, and a min of 6 occurs when t equals 2. Quickie sketch. Can we do a quickie sketch of this one? A little bit. Remember, this has got an oblique asymptote, right? It's got a vertical asymptote at -2, and it's got an oblique asymptote. I don't want to do the long division. That's beside the point. But I do know it comes to a minimum at 2 of 6. So probably the oblique asymptote's there somewhere. It's gonna, when x is 0, what was it? X is 0, or t is 0. The output is 8. So there, 8. I goofed up my asymptote there. This goes like this, and then back up, and I can see on my interval, this would be the 14 has an output of 15. Yeah, it matches my diagram. Isn't that dandy? Okay, there's some homework for you to do. I squished it into one long video. Make up for the last day's class, I suppose. Okay, that's it.